right. So let's see. Today we're going to go over 4.5 and 4.6. I know 2 sections seems like a lot, but we've already started 4.5. And 4.5 is called Power Series as Functions 1. And 4.6 is Power Series as Functions 2. So I think we'll be able to get through the whole thing today. What else? I'm not going to, I don't have an assignment for homework, and I'm not expecting you to turn it in today because the quiz is going to be on, like, essentially everything. So there aren't homework questions that would prepare you for tomorrow's quiz. So you'll have the remainder of the homeworks for the material that's on the test due Wednesday of next week. But you don't have to do any homework this week. I mean, for a grade. You still have to do homework, obviously, because you don't want to fail. As always, I have office hours from 3 to 4 today. I posted all the materials. So you have a practice test on Blackboard. You have a review on Blackboard. You have the answers to the review on Blackboard. And most of the solutions to the practice test are on OneNote already. The last page I still have to work on. We also have a review Tuesday from 1:30 to 3:30 in Baracus room 10 in the basement. That will be a review for every section of Calc 2, not just my students. I won't be there. Your TAs will be running it. And then later that day, I'll have a Panopto live session on Blackboard that will be recorded. So you should try to be there live so you can ask questions and get those answered right away. But it will be recorded so that people can watch it later on Blackboard if they've got a class or something. Yes. Room 10? Today we're going to talk about power series. And just like when I introduced McLaurin series, there's really not a reason to use a separate word for power series. So Taylor series are power series. So every Taylor series is a power series. Every McLaurin series is a Taylor series and thus also a power series. The difference is that when you have a Taylor series, it's a Taylor series of some function that you know, versus a power series, which is just the sum. It's not constructed from some known function. It just exists in ambient space. So today I'm going to go over how to answer questions like this one. Given some power series, and so this is, again, it's not a power series of some known function, it's just a power series. And then we want to know, for what values of x will this series converge? Which is the same as saying, what is the domain of the function defined by this power series? Okay? But we're using the series to define the function. We aren't starting with a defined function and constructing this series. Do you see the difference in how the material is working? So now we start with a sum, we come up with the function, rather than starting with the function and coming up with the sum. Okay, and to do that, we're going to require the ratio test. Those of you who have taken Calculus BC before, this is the only test you will be responsible for test 1. So I know there are many other tests for series convergence. This is the only one you'll need to know for the next 2 weeks. So try not to black out. So the ratio test is actually a theorem about a given series. It doesn't matter where it starts, but the theorem is about a series where the terms are all numbers, so not necessarily a function of x. So the a sub n are real numbers. So given a series, which is the sum of some sequence an, if the limit of the consecutive ratios exists and equals some L, and that L happens to be less than 1, we can say with certainty that the series converges, right? So in the case where that limit exists is less than 1, we know that the series converges. That is what this theorem tells us. If that limit exists, but it's greater than 1, we can say for certain that the series diverges. If it equals 1, we know nothing, all right? We are not going to be answering any questions where the ratio equals 1, the limit of the ratios equals 1. We will be dealing with that in the next few weeks after the exam. So these are the only 2 situations we're dealing with now. Yeah.
So like in the previous slide, it would be 2x or 2x or 3x.
Right.
And they can be any 2 numbers that are in 30 cases.
Yeah. So we'll do some examples. So when I was prepping these slides, I planned on proving this. Will anyone be offended if I tell you that the proof is in the book or on a website, but you're not going to be tested on it? That was my sense, because I did come up with a lot of examples, but then I realized that I omitted half of the important examples. So my timing for this slideshow is off. So let's consider, I'm going to start with sums that don't involve x, so they're just going to be numbers. So we'll do cases where the sums are, where it's a series of numbers, and then we'll do power series afterwards. So if we have a sum from n equals 1 to infinity, 3 to the 1 minus 2n over n squared plus 1. We want to know whether this series converges or diverges, or maybe we won't be able to tell, but we've only got one tool in our toolbox, the ratio test, and when you have a hammer, everything looks like a nail, so we're going to just use the ratio test. So we need to think about the limit as n goes to infinity of a sub n plus 1 over a sub n, and it's in absolute values. In this case, it doesn't matter. All of these terms are strictly positive, but in principle, you're looking at the absolute value. So probably the trickiest part of this is writing out what a sub n plus 1 is. We're just replacing n with n plus 1 for the top term. So it is 3 to the 1 minus 2. So it's 2n, but we're replacing n with n plus 1. So there we go. Over n squared plus 1. So it's n plus 1 squared plus 1. That's the numerator of our ratio. And then the original function, or the original a sub n's, are our denominator. like I said, we don't need to worry about absolute values because this is strictly positive, but this is the first example, so I'm going to try to be particular about it and not make mistakes. We'll see how long that lasts. Okay? Any questions there? Now, because we're looking at the limit as n goes to infinity, right? And infinity isn't a number. Yeah. Otherwise, your idea would be fine. I don't really know. Let's see what happens. I'm recording this, but the recording didn't pick up your question, so that entire conversation is going to be super confusing for people listening later. All right, so I have a fraction over a fraction. So it's a fraction divided by another fraction. When you divide by a fraction, you multiply by the reciprocal. I know that in normal context, everyone would know that, but in calculus context, algebra doesn't make a lot of sense. And now, normally I will omit this step, and I'll put the numerators in one fraction together and the denominators in one fraction together. So normally I will write 3 to the 1 minus 2n minus 2 over 3 to the 1 minus 2n times n squared plus 1 over n plus 1 quantity squared plus 1. Okay, because the numerators are going to relate to one another and the denominators are going to relate to one another. So you might as well group it that way. Then we can simplify. The 3 to the things. The 3 to the 1 minus 2n's will cancel, and I'll just have 3 to the negative 2 in the numerator. And then the n squared plus 1 over, and when I expand that, I'll get n squared plus 2n plus 2. Trying to shrink this and move it around, but it is very difficult for me to get exactly what I want to move around in the lasso. There we go. Now, as n tends to infinity, this fraction just goes to 1. It's a degree 2 polynomial over a degree 2 polynomial in n. So as n goes to infinity, we just go to leading coefficients. You could do L'Hopital's rule twice if you want to, but a polynomial over a polynomial when you have the same degree is going to be just the leading coefficients. So this whole limit goes to 1 over 9. My hot take is that this is less than 1. No one's going to ask me about that bit? Okay. And so now, by the ratio test, this series converges. How does that make you feel?
It converges to one.
Huh?
It converges to one there.
No. No, we don't know what it converges to. Yeah. There's nothing special about L except for it's either bigger than or less than 1 either. Huh? It's what happens when n tends to infinity, yes. Now, Jared brought up a good point. We are not saying that this sum converges to anything. We don't know what it converges to. We are only going to be able to say that geometric series converge to a specific value. We may be able to give upper or lower bounds later, but for now, we aren't saying anything about it.
Well, I'm just trying to think, right away, couldn't you kind of tell that it's going to, the denominator is going to be bigger? Because if we get 3 to the power of 1 minus 2n, for any value that would give you the negative number.
Sure, you can see that the terms go to 0, but you need the ratio of the terms to go to 0, which is a stronger statement. There are a lot of situations in which the terms of the series go to 0, but the limit of the ratios does not. That's a good point as well. So just because the terms go to 0, that does not mean that the series by default goes to 0. We'll see some examples of that. Yep.
And you said that the geometric series are the only ones we're going to see where we can actually find the value of convergence?
Yeah, you'll be able to see for something called telescoping series as well, but in general, it's very difficult to say what these things converge to. All right. Do you want to see another one like this? All right. So here is another example. Again, we've only got one tool, so deciding what to do first isn't very hard. The 1 plus n is the numerator, is the exponent for 5?
If the n squared.
Oh, yeah. So now we are going to look at the limit as n tends to infinity of the absolute value of a sub n plus 1 over a sub n. Because we're looking at the absolute value, I'm going to ignore the fact that the 2 being raised to the power is negative. That isn't going to change anything for us. So I'm just going to say that this is equal to the limit as n goes to infinity, God help me, 2 to the 1 plus 3 to the n plus 1 times n plus 1 over n plus 1 quantity squared times 5 to the 1 plus n plus 1, and that is the numerator of our ratio. I'm totally going to cheat for the denominator and copy and paste, because that's exactly the terms of my series. Yeah. So now I'm going to reorganize some stuff. I get 2 to the 1 plus 3 n plus 3 over 2 to the 1 plus 3n times n plus 2 over n plus 1 times n squared over n plus 1 squared just need one more fraction. 5 to the 1 plus n over 5 to the 2 plus n. Absolute values. Oh. You're about to get here. Some extreme bookkeeping going on. But now, things will cancel. Thank goodness. So I'll be left with a 2 cubed because it's 2 to the 1 plus 3n plus 3 over 2 to the 1 plus 3n. So subtract the exponents. I'm just going to group all of the polynomial terms together. So it's 1 over 5. That will simplify too when you subtract the exponents. And now this guy with all the polynomials, that goes to 1 because of leading coefficients. Again, it's a cubic in n over a cubic in n. Leading coefficients are 1 over 1. So this limit is going to go to 8/5. That's greater than 1. So our series diverges. Questions? Okay. We're all good. You're all making those faces because of how easy all of this is. Let's try another one. Let's try one with factorials. Everyone loves a good factorial. Notice that I don't really care where the sum is starting at because these limits are concerned with what happens as n goes to infinity. So the first few terms are finite. So regardless of what they aren't going to affect whether or not our sum converges. So now I am going to take the limit as n goes to infinity. Over 2 times n plus 1 factorial. And now I'm just going to multiply by the reciprocal of the second term. I'm going to omit that first part. good here. Now, maybe I'll simplify that numerator to 5n plus 6, and then times 2n factorial over 2n plus 2 factorial when I distribute. Now last time they didn't, last time I did this problem, they didn't like me simplifying. They wanted me to explain it, so I will explain now. N's going to infinity. That 5n plus 6 over 5n plus 1, that's just going to go to 1 when we send n to infinity. But the 2n factorial, what does that work out to? Remember, factorial goes 1 times 2 times 3 times, n is going to infinity, so this is going to take a long time, times 2n minus 1 times 2n. But the denominator is going to be the same thing. But we won't stop at 2n, we'll keep going. And now look at all the things that cancel. That's so satisfying. You're dying a cruel and horrible death. Yay. And so now, as I send n to infinity, this is 1 over infinity, right? The denominator is going to infinity as the numerator goes to, or as the first part goes to 1. So this is going to so this is going to 0. Sorry. Again, 0 is less than 1. So it converges. Yep.
So in the case of factorials, is there any case where
What if that factorial had been on the numerator rather than the denominator?
if it's not a denominator?
Nothing grows faster than a factorial. So sometimes you'll have a factorial in the numerator and the denominator, and then it'll take more work. But if the factorial is in the denominator, it's a good bet that you're going to converge. Okay.
How did you just swap the denominators?
What?
Step on top.
Mm-hmm. Oh, multiplication is commutative. So it doesn't matter the order you multiply things in. Be good here. Do you want to see another one like this, or do you want to move on to another one like this? Okay, let's see. What do I want to do? What do I want to do? Okay, here's the next one. Again, that -1 to the n plus 1, right now, that's dead to us because the ratio test, which is the only test we have, is always taking absolute values. So it doesn't matter. So we're taking the limit as n goes to infinity of just 1 over 6 times n plus 1 plus 7 times the reciprocal I'll go ahead and simplify this a little bit just so it's very clear what's going on. So as we send n to infinity now, and if you want, you can do L'Hopital's rule. Taking the derivative of the top, you get 6. Taking the derivative of the bottom, you get 6. So this is equal to 1, which is not bigger than 1 or smaller than 1, so we know nothing. This series, we will learn later, actually does converge, but the reason this series converges is exactly because of the negative 1 to the n plus 1. So the fact that the ratio test only works when you take the absolute value means that if you have an alternating series like that, that's going from positive to negative, something, you lose a little bit of information in the ratio. So my preference is this, but you can use whatever notation you want. I do like drawing boats.
So in terms of graph this, like for the others we can see like convergence and violence.
Well, what? There's no x. This is just a number. So we will talk about what's going on with alternating series. And one of the ways to represent it would be to have the positive series as being like a rectangle with positive height, and the negative terms being a rectangle with like negative height, and then think about things like canceling out like that. And alternating series are particularly interesting for reasons that I will talk about later, but you don't want to know because then it would be able to be on your first test, and you don't want that. All right. How do we feel? All right. So now the question is, why do we talk about this when this section is supposed to be about Taylor series? These aren't Taylor series. These aren't power series. There are no x's. So let us introduce an x. Wait, what happened here? What is this? Oh, here we go. Yay, now we have an x. Consider the power series of blah, 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 blah. For what values of x will this series converge? This was the problem that I introduced originally, and I said we're going to answer questions like this, and then I proceeded to answer 5 questions that were not like this. Yes. All right. I am nothing if not a showman. So yes, what do we do here? Well, it may surprise you, but we're going to do the ratio test. I am not creative. We're going to look at the limit as n goes to infinity of the a sub n plus 1. And now in this case, they're functions of x. You don't actually need to write the functions of x, but I'm just going to highlight the fact that this is a little bit different because it's going to depend on x. X is allowed to be any value you want, but we are going to be taking the limit as n goes to infinity for each fixed x. So we get to pick what x is, but then it's staying put. All right? This is the limit as n goes to infinity. Oh my Jesus. Negative 1 to the n plus 1. n plus 1 plus 1. X to the n plus 1. divided by -1 to the n plus 1, x to the n. We're putting in absolute values, so writing the -1s to the n was stupid. You're not allowed to call me stupid, but I can call myself stupid as much as I want. Actually, you can call me stupid if you want. It won't hurt my feelings. It's not like that time my mom called me stupid. I don't know. All right, let's see. There we go. So this is how that simplifies. When we take the limit as n goes to infinity, we are not sending x to infinity. X is staying put. We are not taking the limit with respect to x at all. So it's okay if our limit is in terms of x, which of course it is, because this n plus 2 over n plus 1, as we send n to infinity, that guy goes to 1. So our limit is exactly x in absolute value. Cool? Now what the heck does that mean? Well, the ratio test tells us that when the limit is less than 1, it converges. And when the limit is greater than 1, it diverges. So when x in absolute value is less than 1, our series converges. When is that true? It's true on the open interval from -1 to 1. All right, so we converge there. We also know that it diverges when x is smaller than -1 or greater than +1. All right? So we know that it diverges on, so it converges, which is all I'm going to ask you about. But on -infinity to -1 open, union 1 to infinity, we diverge. But of course, I have omitted -1 and 1, the places where the limit equaled 1, because we don't know what happens. We have to use a different test for that. And we will, just not in the next week. All right, are we feeling okay? I'm going to do another one like this. You better, I don't have anything else planned. So let's see. Oh, same problem, new series. All right. Whew. Same thing. We're going to think about the limit as n goes to infinity and beyond. Oh wow, I better not put this on YouTube. Disney's gonna sue me. Disney owns Pixar now, right?
Yes. For many years.
Oh, I get it. You guys are young. You think you're so cool.
Avengers came in 2020. This concerned me.
All right, so let's see. I think I've simplified this correctly. But now I need to think about what's going on with this n factorial over n plus 1 factorial. The first n terms of the n plus 1 factorial in the denominator are going to cancel out with the n factorial in the numerator. So we'll be left with limit as n goes to infinity of x minus 1 over n plus 1 in absolute value. Now, I send n to infinity, x can be whatever I want, but once I decide what it is, it needs to stay put. So I have some number that's not changing over infinity, or something going to infinity. So this whole thing equals 0. Again, hot take, that's less than 1. So this is going to converge everywhere for all real numbers on which 0 is less than 1. So are there any values of x that make the statement 0 is less than 1 false? Well, that statement doesn't even involve an x, so it's probably true all the time. So it's going to converge on negative infinity to infinity. We sometimes call this the open interval of convergence. Sometimes we'll ask you for the radius of convergence. So in this case, infinity is the radius of convergence. In the previous example, the interval of convergence was -1 to 1, and the radius of convergence was 1. All right. Any questions?
For this example, could you assume that n factorial over n plus 1 factorial is 0, and then do x minus 1 times 0 and get 0, or is that not?
Right, that's what I did.
Oh.
Right, because n factorial over n plus 1 factorial is equal to 1 over n plus 1. So that's what I did. I said that, well, I had x minus 1 over n plus 1. So as the denominator goes to 0, goes to infinity, the whole thing goes to 0. Yeah. Okay.
And you're talking, you said like as the denominator goes to 0 because that's where the n is, and we're only talking in terms of n.
Right.
Okay.
Perfect. How are we feeling? How are things?
You may have already gone over this, but why is it absolute value?
That's a good question. So I didn't go over the proof of the ratio test, but what it has to do with is it relies on, let me use n rather than I, just to be consistent. This geometric series, and this series converges when r is less than 1 in absolute value, and diverges when r is greater than 1 in absolute value. So that's why, and it diverges when r equals 1 as well, or -1, but it relies on this fact. If
I'm just thinking, like, for the last one, for example, if it wasn't absolute value, then any negative values wouldn't converge.
So the counter example that we want to keep in mind, and we will keep in mind, is the sum of 1 over n versus the sum of -1 to the n over n. Because the one on the left converges, and the one on, the one on the left diverges. The one on the right converges, and for that reason, the ratio test doesn't help us at all. So, like if you tried to do the ratio test here, you would do the limit as n goes to infinity of n plus 1 over n, and that equals 1, but just because it equals 1, it's not specific to the fact that it's alternating, it's specific to the fact that some of the terms are positive and some of the terms are negative, but they don't necessarily have to be alternating. So we just need a whole different set of tools in our toolbox for that.
Okay.
Yeah.
I understand.
Other questions? Say again? So in the case of power series, you'll always have x to some kind of power. Maybe it'll be 2n rather than n, or 2n plus 1 or something. But that's just the nature of power series.
Just as an example, could you do the power series of ln
Yes.
plus x?
Yeah. Is the series alternating?
No.
No, it's just x to the n over n.
It's not.
Okay. Yeah. Yeah. You guys need to have it memorized, but I don't. Alright. So we're going to do the ratio test here. We'll take the limit as n goes to infinity of x to the n plus 1 over n plus 1 times n over x to the n. That will simplify to x times n over n plus 1. And when I send n to infinity, that'll just go to the absolute value of x. So the power series for the natural log of x converges when x is less than 1 in absolute value, so from -1 to 1.
Could you read that up for?
Yes.
If you were to graph this.
Are we sure it's not alternating?
It is alternating. Oh yes, it is. It is alternating.
There we go. There we go. And the reason I knew that is because the natural log, the power series will converge when x equals 1 as well. But the harmonic series 1 over n does not converge, but the alternating harmonic does. Yep.
It's kind of just like a technical question. So like when you're having some problems, like, is it always just asking like when it converges and not like diverges?
So it will ask what is the largest open interval on which the series converges.
Okay, so it's always around
Is this what our quiz is on tomorrow?
Your quiz is on everything but this.
Okay. So like
Unit wise, like every other unit.
Yes.
Okay.
Yeah. So up to 4.4.
from like the beginning.
Yes. There will be integrals, improper integrals. What else is on it? Maclaurin series, and oh, there's one other topic that I forgot.
Error.
Oh yeah, error. Thank you. Yeah, but it's meant to just A, force you to start studying now for the exam, and B, to give you a good idea of what you don't know before you get to the exam. Keep in mind that your first exam is worth 20% of your grade. Sequences will be on the quiz tomorrow, and it will be on test 1. The reason sequences are on there is because it's an easy topic, because we all know how to take limits, and we all have very expensive calculators that can graph things for us to help us take limits.
So the quiz tomorrow is just like last week, but the test is 2 weeks, is 1 week?
The quiz tomorrow is on everything up to 4.4, and the test is everything up to 5.1
When is the test?
next Thursday.
And then, so sequences, is that 4.4?
It is 4.4 and a little bit of 5.1, but remember, it's just the limit as n goes to infinity of an expression
It's
involving
like a
n.
normal, it's just like.
Yeah, just a normal limit. Yeah, so I'm just like trying to give you one easy topic to go with error and Taylor series and power series and whatnot.
Okay.
And I'm putting it on the quiz specifically because if you don't know how to do it, you really need to figure it out before next week, because you don't want to miss the easy points.
So for sequences, like, what would the question ask?
I'll give you a sequence and ask you to take the limit as n goes to infinity of
Could you
it.
do like just an example?
Okay.
Of the sequences?
Yeah.
Yes.
I'm just blanking on what it might be.
So I'm trying to give you the text as you would see it. Determine whether the sequence converges. And if it does, what it converges to. I'm just trying to give you a whole bunch.
This is 4.4.
Yes. Yes. So what does the first one do? Yeah, the first one goes to 2/3. What about the second one? Zero. It goes to 0. Right? Remember what we talked about? Eventually, n is going to get so large that it is bigger than whatever the base of that exponential is. So in this case, n equals 3. And from then on, you have a product of things all going to infinity over a product of things smaller than it. Right? You can think of this as e times e times e times e times ... times e n times over 1 times 2 times 3 times 4 times up to n. And now maybe if the first couple, right, those are things greater than 1, but after that, e over 3, e over 4, e over 5, and so on, those are all values less than 1, so it's the product of a larger and larger number of things that are between 0 and 1 and are also going to 0. So for both of those reasons, this is going to go to 0.
And the next one, cosine and over will also be 0.
Yes, this will also go to 0 because cosine is bounded And n is going to infinity. What about n plus 1? I realized I needed one that diverged, so, but I ran out of ideas. How are we doing?
I just have a generic question. Why does L'Hopital's rule like not work for the two that go to 0? Because when you do L'Hopital's rule for both those, you get divided by 0.
Okay, so the cosine n over n is not an indeterminate form. It's not like 0 over 0 or infinity over infinity.
Yeah, I tried to get that.
And then the second one, it would, but we don't know we don't have a way of taking the derivative as of n factorial in this class. You will, but not in this class. And then it would work. Right. Do you want to see more Taylor series problems? Like the ones we just did. I have like 3 more prepped.
Yeah. Let's do it.
Okay. I actually prepped for this lecture because I'm recording it. I'm going to be famous. All right, here's another one. It's amazing. Again, we've only got one tool, so we're going to use it. Yeah. Does it? Oh, and it's an absolute value, sorry. Absolute values abound. So I get a 2 here, and then the numerator is the x plus 2 to the 2n plus 3 over x plus 2 to the 2n plus 1. So I get an x plus 2 squared in the numerator, and then everything in the denominator will cancel. Right? So I get that. So I need 4, and then this equals 2 times x plus 2 squared. I'm going to throw it in absolute value even though it's always positive. And now this needs to be bigger than -1 and less than 1. So -1 over 2. I'll take the square root of both sides, I guess, but I'll end up with -1 over root 2, which I have to do because it's an inequality, is less than x plus 2 is less than 1 over root 2. So 2 minus 1 over root 2 is less than x is less than 2 plus 1 over root 2. So the radius of convergence here is 1 over root 2. Cool? Cool. And this will end up diverging at both of the endpoints, I think. Any questions on that? What are what?
Why don't you subtract the 2? It's x plus 2, and why don't you subtract the 2?
Oh, thank you. You're 100% right. -2. Goodness. 100% right. It's still 1 over root 2. I just messed up where it was centered around. Okay, is that all right? All right. Well, we only have 5 minutes left, and I don't want to try to rush through another one in 5 minutes, especially because the next one's kind of messy. So I will stop it there.
Yeah, I guess